Hello everyone, and welcome to the third webinar in the latest Lab Automation University online series. These webinars, as you know, are a joint educational program of the Institute for Laboratory Automation and Lab Manager magazine. Once again, I'm Kaylee Thomas, the Events Manager for Lab Manager magazine, and I will be moderating today's webinar, which will focus on options for improving productivity. As you know, we like our webinars to be interactive, so we encourage you to send us your questions at any point during the webinar, and our speaker Joe will address these during the question and answer session following the presentation. To ask a question, simply type your query into the question box on the right-hand side of your screen in the GoToWebinar software. We will try to address as many questions as possible during the question and answer session. With that, let me introduce our speaker, Joe Laskowski, who is currently the Executive Director of the Institute for Laboratory Automation, which is a nonprofit organization focused on the development of people and technologies to effectively design and implement laboratory automation and computing systems. Welcome, Joe.
Hi, thank you. And welcome to the third series in Lab Automation is Inevitable. Are you ready? As Kaylee mentioned, we're going to be focusing on the options for improving productivity. When we get involved with automation, there are three reasons we do it: increasing productivity, adding new capabilities, and looking at more sophisticated techniques, particularly hyphenated techniques, where we're joining multiple technologies together into one system. And these apply to any type of laboratory, whether it's research or testing laboratories. In this session, we're going to look at the technologies that can be used and their impact on productivity. We're going to look at it from a couple angles. One, what the technologies are. Two, how they relate to productivity, because they don't all do it the same way. And finally, how you can use them in combination to accomplish different aims. We'll also take a look at how to go about beginning planning. The first thing we've got to deal with is what improving productivity really means in your lab. There's a list on the screen that gives you a whole bunch of possibilities. What the right way to do, or what the right answer is, depends on your laboratory and is going to vary from one organization to another. The answer really depends on the kind of work you're doing and what kind of pressures you're seeing right at the moment. Test processing is usually a component. We'll begin by looking at improving sample throughput. Now, one obvious way of dealing with sample throughput is to simply hire more people and get more to do more work. And if that were a realistic consideration, we'd be done. You can go back and have lunch. But let's move on to machine-oriented systems. The first way we'll look at it is taking care of sample preparation using automated systems. When we do this, we have to deal with the cost of the system and training, but we get some benefits. Production can move from single shift to multi-shift operations. You can increase the capacity of the equipment by making equipment changes, or by replicating the system, wind up by doubling the capacity of your system. So it's not a matter of simply adding people, just adding equipment. And there's a side benefit to doubling the system in that you have a backup system in case anything goes wrong, or one system has to be down for a period of time. In the last two sessions, we've made references to three classes of automation systems: computer-assisted lab work, scientific manufacturing, and the one that really deals with the kind of thing we're talking about now, which is computer-controlled processing. In addition, when we take a look at the elements of lab technology management diagram, we're going to focus in on one part, and that's on robotics. There are three ways of looking at robotics: turnkey, purpose-built systems, ones that are designed to do a specific job and do nothing else; configurable systems, which have pretty much a set group of hardware, but can be changed by making some simple software changes; and then user design systems, where basically you build it. And we'll start there, because historically, that's where robotics in laboratories began. When robotics began, we were looking at three vendors: Zymark, PerkinElmer, and Hewlett-Packard. And just for historical purposes, Zymark was purchased by Caliper a number of years ago, and Caliper was just recently purchased by PerkinElmer. So PerkinElmer, who got out of the robotics business for a while, is back in it. The images on the screen show two different styles of robotic systems. The center one is the one that was used by Zymark. That's this system here. Their idea was to have a centralized robot which had an arm that would go up and down and spin and rotate in 360 degrees and have all of the equipment that was being used by the analyst set up around the robot. The other format was to put the robot on the edge of the lab bench and have it run up and down the lab bench, have access to the full space on the lab bench, and work with any equipment that they needed access to. Those systems really didn't produce the higher productivity that people wanted. They could be used to do the job. They offloaded people's tasks, but they really didn't do much in the way of improving sample throughput. The reasons for it was the people that engineered the systems, that put the systems in place, thought, well, somebody, the analyst, does the process this way. We'll make the robot do the same thing. So instead of a human being walking up and down the lab bench, the robot did it. Or instead of somebody going up and picking up tubes, the robot would go off and do that. So the amount of time that things took was about the same. We didn't get faster throughput. We just offloaded people a bit. Systems need to be engineered, and the systems need to be analyzed and engineered to really work to get productivity gains. So the problem sources were things such as the one shown on the screen. The processes were not well understood. They took an experimental approach instead of a process engineering approach. They basically tried to implement things piecemeal, try things, see what worked, and then move on to the next part. When in reality, when you're dealing with systems like this, you really need to analyze the entire process and plan it and engineer it from start to finish. Also, the potential for automation was not well determined. If you look at this part of the image, back in here, you'll see some little stands. What those were gripper stations. When the robot needed to work with a different piece of equipment that the current gripper couldn't handle, it would change grippers to a different one. So the robot was constantly adapting itself to the type of hardware and equipment that was being used, which might also be used by a human being, instead of having equipment that was designed to work in robotics applications. There was always a need to make equipment adaptations and working with systems. Too often, the products that were developed for laboratory applications by third parties were really a combination of products, different pieces coming from different vendors, and this created another problem: support issues. The system may work well when it was first installed, but when any one of the components was upgraded, you ran the risk of having the entire system fail, because the upgrade somehow may change the way the system would work, and as a result, the entire system wouldn't work together. That's changed. The most notable example we have for laboratory robotics is the autosampler that we use to take vials, samples, and introduce them into chromatographs or other devices. But areas in life sciences have even more robust techniques for dealing with robotics. The diagram in the upper left-hand part of the screen is an illustration of a microplate, or sometimes called a microtiter plate. It's a fixed geometry plate, and this one, the one that's depicted, has 96 wells. Each well acts as a sample chamber, and the ones that are being developed now are starting to run in the thousands. What's been done because of the standardization on these plates is that instead of having samples being analyzed serially, one at a time in a train, the samples are being analyzed in parallel. A whole group of samples is being processed at one time. And because of the standardization, we have things like liquid handling workstations and plate stackers that are designed to go off and work with these things and work with them very efficiently. Another example of robotics is put out by Agilent. It may not look much like a robot. Basically what it is a very sophisticated autosampler. And the autosampler, though, instead of just taking a vial and introducing it into the chromatograph, has the capabilities that are shown at the top of the screen. You can go off and dissolve a sample, you can dilute it, you can add internal standards, you can heat it, mix it, a whole bunch of things. You can do in a very small footprint work that may have taken a 4x8 space, 4x8 foot space, using something like Zymark system or one of the other early robotic systems. So here you have a fixed piece of hardware that has a lot of capabilities. It simply needs to be programmed to do what it needs to do. And if you change the analysis, change the programming, the same piece of hardware works. So robotics is advancing. We also looked at this system last week as an example of the kind of equipment that's being used for doing PCB analysis in food products. Basically, it's a small chemical engineering system that processes the sample and gives you the results. Successes in robotics are based on really understanding the process, on process engineering, determining whether or not automation is possible and making sure that the stuff works. The products that we looked at are products that were designed for commercial applications. They had to work together, so everything had to be integrated and make sure that it worked well. The equipment was adapted to fit the applications and the components integrated. That's the kind of approach that we need for successful robotics and successful automated sample preparation. So we have a situation now where we can take samples and we can prepare them. Now we're going to have to deal with a lot of data. And the next step is to deal with data stations to offload calculations instead of people doing the work, and also cooperate with the auto samplers to make sure that the data acquisition and the sample introduction are being coordinated. In doing this, we're making a fairly significant change. We're moving from the hands-on science realm that we were used to and trained in school to the digital realm, to working with information and working with data and working with control systems instead of doing all the analysis and the work by ourselves. And for many people, this is a significant departure from what they're used to. It brings us into the realm of informatics, where we talk about things such as scientific data storage systems, guided execution systems, electronic laboratory notebooks, laboratory information management systems, and multi-instrument data systems. We looked at this diagram back in the first week of this series, and we looked at when various technologies came into place and then took a look at how they evolved over time. So we're going to begin by looking at the instrument data systems, which occurred in the late 1960s by PerkinElmer. They were one of the leading proponents of these systems. And those systems can be used in research and development testing, and quality control applications. And like document management systems, they're fairly general. They can be used in any application, and actually today, for the most part, people buy the instrument and the computer system together as one package and don't even think about the fact that there's a distinction. They're really dealing with different things, one working in the analog world and one working in the digital world. If you want to go off and do a bidder evaluation, you can decide what kind of instrumentation you want to deal with and then pick up data systems that are better suited to your type of application. The typical computing model that was used for these systems was one computer tied to one instrument. The transmission of the data from the instrument to the computer was done either over analog or serial lines usually, or in some cases parallel information. Some instrument data systems will use the IEEE 488 bus, but that is pretty much used primarily in electronics applications and electronics laboratories, working with oscilloscopes and similar types of equipment. DuPont was one vendor who tried working with the IEEE bus in some of its lab instrumentation, but that didn't last very long. In many cases, the systems came with the analysis software, but in some cases, it was up to the analyst to go off and provide it, and that led to the development of the first electronic laboratory notebook by a company called LabTech. This was back in the 1980s when they came out with their system, and it was designed for doing data acquisition and experiment control, primarily using serial or RS-232 interfaces between the computer and the instrumentation. It was designed to allow somebody to set up all the communications protocols, execute the experiment that had to be executed, acquire the data, and process it. This is another way of looking at laboratory computing. We have 3 levels, and on the bottom we've got all the equipment that sits on the lab bench. In the middle we have the departmental systems, the large database systems that the entire laboratory would have access to. And then we have communications going off to other laboratories if you're in a research environment, or process control, warehousing, if you're dealing with a manufacturing environment, and also work that's being done by IT services. So we can look at how in terms of data systems, how the equipment lays out. And the system we just looked at, the computer and the instrument here, would sit on the lab bench. But that's being replaced. In today's systems, we still have those available, but we're also looking at either integrated data systems and computers where everything is really in the same set of skins, or a distributed approach to data acquisition using subsystems. This is another example of instrument data systems where you have multiple instruments being supported by multiple users, all in the same part of the same network package. All the applications work here. The database works here. The data from the instruments comes into it either over communications lines or through a separate computer system. The advantages of a system like this, particularly for something, this occurs very frequently in chromatography. Justice Chromatography is one example of it. Varian had the same type of products, and as well as other vendors. It allows you to consolidate all the data for a given type of experiment, different type of instrument, in one place. Think about a lab that has 4 or 5 chromatographs and independent data systems for each one. If you wanted to look for the data on a particular sample, you'd have to visit each one of those stations. Here, it's all put in one place. So the data is consolidated, so you get higher productivity because it's easier to work with. You get improved management of the information. You have remote access. So if you're working from home or outside the laboratory and you want to find out how your work is going, log into it and take a look at the data. And these systems also contain a rudimentary laboratory information management system. They'll track samples, they'll track users. So you can actually, if your laboratory all has one type of instrumentation, a system like this might be all you need to support it. You can do all the sample tracking, logging, data acquisition, data analysis, all from one platform. Coming back to this diagram, when we looked at the adoption of technologies by different systems, around the year 2000 we started seeing these things split off or take additional capabilities, where a single data system was now a multi-instrument data system and picked up sample tracking capabilities. In terms of how the hardware actually lays out, it looks something like this. The data analysis and management system reside on a departmental system, and the instrument system still sits on the lab bench. And again, it can either be an instrument tied to a computer, or it can be a completely isolated subsystem where there is no computer except for the database system and the computer that the analyst uses for doing the work. We can tie these systems together to get better performance. So the sample tracking system can be tied to the data system, and you wind up almost with an assembly line, everything going from sample preparation through the analysis of the completed results. And that's what we're talking about when we look at the scientific manufacturing and production systems, where you're doing all of the work that needs to get done and loading it all into the final analysis system. In order to do that, we need a different model for how we work with things, and that's what this describes. We have sample preparation, the sample introduction, the instrument, whatever it happens to be, doing the work that it has to do, data analysis, reporting, and storage, but we need this loop to make the system work, a control response loop. The computer system and the sample introduction system, the auto sampler, have to be coordinated. They have to agree on when something's getting done. Use chromatography again as an example. If all the data for a given chromatogram is measured from the injection point. So the computer and the auto sampler have to agree on when that ejection point is, otherwise the data is going to be erroneous. So in all the systems where we deal with this kind of workflow, we have to have coordination between the sample introduction and the data system so everybody's working with the same set of information, including perhaps reading barcodes to make sure we know what the sample is. One way of packaging these types of products occurs in life science examples. These are products from two different vendors doing an immunoassay analysis. And when immunoassay analysis first began, you had a number of pieces of equipment set up for doing pipetting, washings, adding materials to it, possibly heating and aging the sample, and then making the readings. And here, everything is done in one compact package. Prepare the initial samples, put them in, add the reagents, and the machine does all the work, including doing all the readings on the plates. So when we start talking about sample preparation and integrating systems, you don't have to have these things spread over the lab bench. If we've standardized properly, we can do it in fairly compact footprints. One point that has to be addressed when we start looking at samples like this, and as we move into the digital realm instead of just working with our hands-on equipment, is the ability to properly manage and understand how to use these systems. This is an article that was published in March in 2005 on chromatography, and if you look at the yellow area on the bottom, the author talks about the fact that even though people are well schooled in how to do the analysis, they don't understand how to deal with the data. They don't understand how the computer system draws baselines, carries out the analysis, how the work is done. All they know is the signal goes in one end and numbers come out the other. And that's not an isolated case. This is a summary of a symposium that was published in American Laboratory in 2011, September of that year. It says, even today, the instruments are often more sophisticated than the average user, regardless of who they are. You simply don't have the full backgrounds to deal with the products. And this problem isn't limited to chromatography. There was a meeting held in Hamburg in May of 2012 where a vendor stood up and gave a presentation talking about their equipment, but also talking about the kind of problems they encountered as they went from one laboratory to another. This was liquid handling equipment, and people were getting erroneous data, not because there was anything wrong with the equipment, but because they hadn't been calibrated properly. The volumes were off, the dilutions were off, and the results were junk, simply because they didn't use the equipment properly. So if we're going to get into the area of informatics and looking at these types of systems, we have to make sure that people are properly trained. Now we'll move on to looking at productivity of laboratory work itself. This is where the next level of laboratory informatics comes in that we noted earlier. This is where we start looking at laboratory information management systems and electronic laboratory notebooks. These systems do nothing for us in the way of sample throughput. These are administrative systems. They offload administrative work. They can guide the process execution of tests, but they don't improve sample throughput. And as such, they come under the heading of computer-assisted lab work. None of what's being discussed here requires a computer, as data acquisition did, but the computer system simply makes things a lot easier. These products are really addressed at different sets of problems. Often in symposia and meetings, you'll have people talking about, well, gee, I don't know if I need a LIMS or electronic laboratory notebook. That really isn't, that kind of question really says that they really don't understand the products, because these things are really geared towards different types of situations. For example, laboratory information management systems are built around a process. There's a process that goes on in testing laboratories. It involves the samples being logged in, making sure the samples have been received, the ability to generate work lists. You're going to carry out a certain test that day. You want a list of all the samples that have to be done. Listing should also include where they are and what the priorities are. You also need the ability to enter data and do reviews and approval and finally get the results out. So there is, for any type of testing laboratory in almost any industry, The process is the same. Samples come in, samples are processed, results go out. That's the basis that LIMS systems use for their development. Their role in improving productivity reduces paperwork. It makes it easier to find results, easier to find samples. When I was doing analysis work, we didn't have a LIMS. We had paper. We had log books, and we had sample request forms. And we spent a lot of time running around the lab trying to find out who else was working on the test and where the samples were so we could do our work. The system should tell you that now. You can generate work lists, produce reports, and basically manage the lab's workload very easily using one system. And systems can be optimized for certain types of applications. For example, there are specialized versions of LIMS systems for doing water testing, stability testing, and formulation testing. And we'll look at just stability testing for a moment to see how that works. When you do stability testing, you're looking to see how a product survives over a long period of time, basically determines shelf life. And it may be a matter of how long it actually sits on the shelf or how it stands up to weathering conditions and what happens to that product over a period of time. So in order to do that, you've got to set up a whole regime of testing. You have to expose a sample to whatever environmental or accelerated aging criteria you have, aging methods you have, and then periodically do testing. So you've got a range of samples becoming available at a certain time and a range of testing that has to be done in each one. And in most LIMS systems that are not specialized, every sample would be logged in individually. And you'd have to keep track of which samples were tied to what sample IDs. With a stability testing system, it'll do all of that for you. You lay out the program, it'll identify the samples, make sure things are well organized so you can work with the data and take care of it for you. So that's just one example. Electronic laboratory notebooks are a completely different type of system, dealt with a different type of problem. They're originally designed to mimic the behaviors of a paper notebook. As a matter of fact, there are some people that use Microsoft Word as an electronic laboratory notebook. It can be used for bringing in text, charts, video, audio, almost anything you want to deal with. And actually, if in a very simple way, it can be used as an effective system. But unlike LIMS, there is no implied process for the use of electronic laboratory notebook. You really have to understand how you want your laboratory to work and how this product is going to fit into that work. Lab notebooks are places where you can capture data. They can help you provide regulatory compliance because it's easier to search and find information. You have a number of different types of inputs that are possible. There are some symposiums that are talking very much about the use of tablet input, not just for test data, but for animal experiments. For example, if they're going out and working with a bunch of animals, they can get the data from the animal, log it in through the tablet, and also photograph the animal so they can get a good idea of its ID and what its condition is. You can bring information in from different types of instrumentation and record all that, and then also have access to the internet to bring in information from specialized databases. So it's things that you could have done manually. It just makes it a lot easier to deal with. It also makes it easier to share the information, and the layout can be very flexible. When we talk about laboratory notebooks, we're talking about basically three different types: general purpose, discipline specific, and a third one called scripted execution, which some people are describing as electronic laboratory notebooks, but other vendors are trying to move it away from that. VelQuest, which is now part of Accelerus, originated the idea of scripted execution systems. They originally had them as being electronic laboratory notebooks, and now we're trying to move them out of that realm and differentiate them. If you want to learn more about the products, the two references on the screen are really good ones. Atrium Research provides some good reports on different products and what's happening to them. Scientific Computing World over the past several years has done a summary of laboratory informatics. So if you want to get an idea how things are trending, it's a good place to look. And they've recently come out with a guide to the smart laboratory. This is a European publication. It's well worth looking at. if you want this kind of information. We talked about general purpose ones, which basically something like Word or something else is somebody just catching all the information you want to put in it. Discipline-specific ones have links to specific types of databases that you might use in your work. For example, if your work is being done in biology, they'll have links to biological databases. If your work is being done in analytical chemistry, you'll have chemical structures. You'll also have reaction databases. You'll have access to test information. The scripted execution systems are often not well understood. The purpose of a scripted execution system is to help a person carry out a series of tests and make sure that all the tests are validated and clearly recorded in carrying out their work. These are ideal for regulated environments because when you're done, you've got all the information you need to support procedure that's been done and back up the results you're dealing with. So you start off by starting the procedure, and the first thing it does is verify the analyst. Has the individual that's doing the work been trained for it, and are they qualified to do the work? Then you go through and you verify the equipment. Is the instrumentation that's going to be used, for example, been calibrated recently? And is it certified currently for use, or is there a problem with it? Are all the reagents current? Are they out of date? Have they been tested and evaluated recently to make sure that they are what they're supposed to be? And then it brings you through a step-by-step execution of all the test work that's being done. If you're doing weighings, it will record the information from the balance. Or else if you can't do it automatically, you enter it in manually. Imports instrument data from a variety of sources and then generates a certified report. But it's all geared towards work for a human being to work. It doesn't work with automated systems. So scripted execution systems really document the process of doing a test, record all the data, make sure that all the reagents and equipment is appropriate for the purpose it's being used for, provides links to other systems and devices, and is really geared to supporting regulatory compliance. The functionality for this type of application is available in both standalone products as well as capabilities that have been added to a laboratory information management system. The specialized products are standalone. They do their work, but they can also communicate to another system. You just have to make sure the integration works. In some cases, do the programming. But the nice thing about them is that the templates are there for you to do all the procedures. Many of them come with procedures already built in, but if you've got to add your own, there's usually a fairly simple way of getting that done. The stuff that's available in laboratory information management systems is quite a bit different. It provides the direct links to everything in the LIMS system, so all the data you need to work with is there. But they're a bare-bones system. You have to do all the programming. So it's a trade-off as to where you want to spend your time and your efforts. So an ELN's role in productivity is much as the same as it is in the LIMS system. They're just dealing with different applications. It reduces paperwork. It makes it easier to find results, which is very important if you're dealing with intellectual property concerns. It documents the works, provides links to databases, produces reports, manages experimental data, but it really does it in a different way, in a completely different environment. One is a human-centered environment, the other is a process environment. Scripted execution systems provide higher quality data, not because the numbers are any better, but simply because you have more backup and more support for the data that you've recorded. Provides regulatory support and also reduces the administrative workload. So when we look at these things, we're not looking at a case of, gee, can both of these be used for the same type of application? They really deal with different types of problems. You've got to make sure you understand what problem you're dealing with to choose the right application. So now we'll take a look at how these things might be used in different types of applications. We've already looked at this portion of it. Data's coming in from the instrument. And in a research environment, you might originally do your record keeping, the stuff that's part of an electronic laboratory notebook, in a paper notebook. But as that becomes more cumbersome, and as long as you start dealing with other issues such as intellectual property management and the ability to share information, you may want to move over to an electronic system. In some laboratories in research environment, they do a lot of sample tracking and work list and work management. In life sciences, it's areas such as high throughput screening has this type of issue. In physical testing laboratories, it's stability testing or formulation testing that has this type of work that's being done. They may work in concert with a test or experiment execution system if a lot of the work is being done manually. But the focus of everything comes back to the notebook system, whether it's paper or now primarily electronic systems. So there is a role for both as long as there's a need for both. Again, here you're dealing with a large volume of testing that has to get done. If your testing volume isn't particularly large, you're better off with this kind of a system. When we look at quality control laboratories, we see a completely different environment. We can come back here and use paper notebooks for recording results, but the heart and soul of a testing laboratory is going to be this system, the sample tracking work management system, or was commonly referred to as a laboratory information management system, because you're dealing with a very large volume of work, large volume of testing, usually a fairly standard suite of testing, and everything's got to go in there. The sample logins, everything revolves around that part of the process. The rest of it is support information. So the lab notebook may be used for recording information, both whether it's electronic or paper, and again, now electronics preferred because it makes it easier to connect these systems and work with the data. These systems, scripted execution systems, may be usable, but only for a limited time. It may be a temporary solution as you implement a full automation system. As soon as you start dealing with automation, the need for these systems goes away. So it's questionable as to how important they're going to be for your laboratories, for this type of laboratories application. When we start looking at testing R&D laboratories, we see different types of problems. They deal with both routine and non-routine testing. They also deal with method development. And just as the quality control laboratory had a need for both starting off with a paper notebook and then moving off to an electronic system, we see the same type of thing here. This end of it, right, is the same as the quality control system. This one you might need a specialized notebook, type of electronic notebook, that provides better support for method development. These might be variations on the same product, or they might be two completely different products. Here, again, the heart and soul of the laboratory is a sample tracking system, as opposed to the research system where the heart and soul of it was really the notebook. A text execution system may be usable because the work that's doing in this type of laboratory is varied enough that full automation may not be possible, or cost effective. So we have a range of capabilities, and we can get some benefits by tying all three of these systems together, as shown here. The benefit to this last step is to offload the administrative work that people are doing and get the results from the instrument data systems directly into the notebook, the laboratory information management system, and provide some better administrative support. You offload things such as transcription errors, the need to go off and cross-verify data. So you get more efficiencies there. So we can take combinations of computer-controlled processes, such as sample preparation system, and computer-assisted lab work systems, timed together to provide a full scientific production system. So the question is, what do we gain by adding informatics to the sample prep system? Well, we reduce the administrative workload. There's a shift in the nature of work. The work is less interaction with experimental details and more systems management. We get higher throughput, less involvement in terms of people, but the nature of the work changes, and that's what we talked about in the last session. Making these systems work requires engineering. You can't do it on an experimental basis. It's not a case where you really want to go off and say, well, we'll try this, we'll try this. will fix this bottleneck and will make the other systems work later on. You really need to start thinking about these systems as a complete system and working with them and engineering them to work together. You also have to make sure that the people that you're dealing with are trained to work with the systems effectively. So the next question is, how do you get there? How do you go from all these types of systems and do the planning that's necessary to make these systems work? One of the things we've been working on for the past couple of years is something called the development of a laboratory automation architecture. It's a basis for putting systems together, for planning systems that work, everything from policies and practices that you need to go off and support the development of these systems to workflow models that can be used to illustrate how laboratory work is done. The policies and practices portion we'll be covering in the next session on November 6th. There we'll be talking about management's role in lab automation technology management. The next thing we want to look at is workflow models to help illustrate how these systems are working together. And this is the basic model that we use in our work. It might describe one individual or it might describe a group. Each one of the ovals is a database. The arrows represent processes that take information from one database, operate on it, and then store whatever came out of it into another database. And this, for example, this arrow is the measurement experiments process. One of the things we talked about earlier is that our definition of laboratory automation is that you automate processes, not instruments, and this is where this process arrow comes from. So the information that the analyst needs to work with comes out of this database. All the work that gets done on the lab bench goes here, and the resulting information winds up in another database. If you're doing a laboratory system that existed, say, in the 1960s, that database would be your notebook. Today, it's computer systems. And that workflow model we looked at looks like this. We've got the sample preparation system, the auto sampler, the instrument. The computer system straddles this entire area, from doing data acquisition through storage, and as you'll see in a moment, analysis. And we also have the control response loop as part of the system. The computer system now would go off and take the data that's in its database, perform an analysis, and then put the results in the information database. Again, in the 1960s it was paper. Now it's either an electronic laboratory notebook or a LIMS system. And finally, in research applications, we take information and synthesize it to create new knowledge. This wouldn't exist in a quality control laboratory because they really create new methods or new knowledge. They're basically a testing organization. So let's take a look at how that works in a testing laboratory. They have common sets of characteristics. They occasionally develop new tests if it's a research and development function, but not in quality control applications. They run a fixed suite of established procedures on a limited range of samples. Their primary product is information, usually discrete sets of values, that are sent back to whoever submitted the testing in the first place. They're also subject to regulatory requirements, and those regulations may be in origin from ISO, from the FDA, from the EPA, and in some cases more than one. And this is how we start looking at products and laying those out. We have document management systems here, test, experiment, and test execution systems here, instrument data systems down in this base, and then a laboratory information management system, which is the heart for the testing laboratory. Sample submissions come in and test results go out. The knowledge database is obviously an important one. That's where all the documentation for the laboratory exists, where all your test methods are. It has to maintain a revision history for all the documents, links to supporting information. If you're dealing with hazardous materials, you have links to those supporting those things. Registries of people that are qualified to do the testing. This is the same sort of thing we saw in the test execution system. Documents that provide repositories for resolving issues or suggestions for improvements, and also all the things that you need for supporting ISO 17025, the ability to track complaints, non-conforming testing, calibration issues. We're starting to see these things, or have seen these things, affect products such as LIMS systems, where LIMS was primarily dealing, or initially starting in this range of tasks. It's expanded to deal with instrument data capture, and it's also taken on, in some products, taken on the role of document management. So all the things that we talked about in the knowledge database can be taken care of by the LIMS systems. One of the questions that you need to deal with is how much of your laboratory do you want focused on one vendor? How much do you want to have your laboratory really controlled by one vendor's set of products? That may provide a better means of integration, but it doesn't mean you're going to get best of breed. And in terms of the data database, this is an example of one of the issues you have to deal with. If we're dealing with chromatographic information, it has one set of databases. If you're dealing, in this case, with a 3-point bending stiffness test, which is a physical properties measurement, it's going off into a separate database. When you start looking at these things, every data system has its own database, and you've got to start looking at how many databases you actually have to manage and support and back up. Ideally, we'd like to see all of these things tied into one system, but we're far from being there yet. Until the standards for data format standards are done, this is going to be a long way off. But it also shows that you have different paths for dealing with the analysis of the data, both mechanical and instrumental analysis, going back into the LIMS data system. So you have multiple streams, multiple databases, and ideally when you start looking at your laboratory, you want to try and minimize those as much as possible. We can also use these diagrams to show how things are working between different departments in the organization. For example, if you're dealing with a manufacturing organization, here we have a quality control laboratory that's doing testing work. The results go off to both process control and shipping. So if you're looking at an integration program, if you're looking at the purchase of a LIMS system, you can look at how these products are going to go off and affect the productivity not just of your laboratory, but also the productivity of the other organizations. If you can speed information flow from the laboratory into process control and shipping, it means you can get products out faster. It also means you can provide tighter control of the process and provide higher quality products. We looked at this example in research as one way of understanding how all these products fit together. In terms of the diagram that we have, this is how it lays out. Each one of these represents an individual researcher. They're working with a common data set and a common knowledge base. Basically, it means that there's a common repository for all of their documents, and that there's common repositories for all of the laboratory data that they're working with. This is the testing portion where the LIMS system would be appropriate. And if we look at that diagram and start laying products out on it, we can see how the products lay out and how they fit and how they're allocated. We can also see where there's redundancies. For example, here we may have the same scripted execution systems as taking care of that process. It may or may not be the same as this system, depending upon the nature of the work that's being done. If a lot of this is automated, you may not even need the system. It also shows the need for not only having a data system connect to the LIMS system, but also have the LIMS system go off and send data off to the LN. So this is an example of really how you can lay out a laboratory and really get a better idea of what your product requirements are. These diagrams can also describe how you want your hardware systems to look, which ones you want to have as being departmental systems, which ones you want to have as being systems on the lab bench. And in laying these out, basically the application should dictate the layout, not the other way around. And it also means that you're going to be working with the IT groups. You may want to create a scientific or lab IT function to work with your people in your laboratory to make sure these things are really implemented properly so you can get the productivity you want out of them. So how do we deal with these things? Well, there's some simple questions that you can ask. Can the process be automated? Can it be done at a reasonable cost? And how difficult is it going to be? Not just to deal with the integration portion, but also supporting and upgrading it. And finally, is it really worth it? As far as whether or not the process can be automated, you have to look at a really good description of that process that you're working with. And that description isn't just the one on paper. You need to go on, whoever's going to do the implementation and manage the project needs to follow people around that are actually carrying the process out, in case they find things such as little fixes that aren't recorded, little tricks in getting the work done that mean the difference between a process working and not working. And also in the material handling process, on both the equipment that you're working with, can it be converted at reasonable cost, or does it have to be converted at all in order to make this system work? Has this system been designed around people and not around robots? When you're looking at costs, you have to look at equipment costs, the cost of redeveloping methods. If you're going to implement an automated system, you want to optimize it. And that may involve some redevelopment costs of the method. You simply can't just take what people are doing and translate it to assume it's going to work. You've also got to figure out the likelihood of success, the training requirements, and the phase-in process. At some point, you're going to have the way things used to be done, and when the project is completed, the way things are going to be done now, and make sure that that transition is done cleanly. Planning is essential. If you're going to do a stepwise implementation, you should plan the full project out as though we're going to be done all at the same time, and then go back and implement things a step at a time, but making sure they fit that framework so that things can be integrated and tied together. You also have to be prepared for technology changes. And I'm not going to go into this now. We're going to be covering this in the next session. But this is a product lifecycle diagram. It's probably a lot different than you may have seen before because it looks not only at upgrades to products, but the generations of the creation of new generations of products, and considers what happens if a product is retired. All those things have impacts on your laboratory, and you've got to take them into account. So you've got to plan for flexibility and continuous improvements of these processes and how they're being implemented. And also make sure you know who's going to provide the support, training, and ongoing maintenance. So is it worth it? Well, what are your criteria for success? What are you trying to get at? And when you do this, you need to look at all of the alternatives for producing what you want to do. An automated system is one approach, but so is outsourcing, or maybe temporarily hiring some additional people. Is this problem that you're trying to deal with a temporary spike in samples, or is this the leading edge of a much bigger problem that might justify automation? You've got to look at it because the people who are going to be approving your project are going to be asking these questions. You may as well have the answers for them. And then when you're working on the project, make sure you build in test points to check for delays and evaluate the project's effectiveness. So there are a number of reasons for dealing with automation that apply to any laboratory environment. Your ability to reach these goals really depends on planning, understanding the technologies in the laboratories, and how they can be applied to your lab. The next session, as I mentioned, is going to talk about management issues, policies, and practices. And we're going to be looking at these types of elements: managing assets, intellectual property, process management, validation, security, IT, the whole range of things. So that's where we're going with this. Any questions?
Hi, Joe. Yep, we've had a few questions that have come in. One of them is, can you give an example of where instrument settings can adversely affect lab data?
Yeah, I'm going to use chromatography only because it's an instrument that I'm really familiar with, and it's also probably one of the most popular instruments that exists out there. There are parameters that you can set on the computer systems that control, for example, where peaks, where baselines are being drawn. You may have chromatogram, the peaks may be resolved to the baseline, have baseline separations, or they may have a valley between them. And depending upon how you set the parameters will change on how those baselines are being drawn. The right set of parameters means they're being drawn the right way, The wrong set of parameters may mean that the areas under the peaks are being misallocated and you're getting the wrong results.
Okay, excellent. The next question is, why is integration of instrument systems as big a problem as it is?
There are basically two reasons. One is the lack of standards, and this is something we're going to be beating on over and over again. We need two types of standards. We need standards for communication between systems, and then standards for the content of the messages, basically data format standards, that allow systems to exchange information from different types of instruments effectively. The other part of the problem is something that the vendors have to deal with. When a vendor comes out with a product, he has to assume that there's nothing else going on in the world, that his product is going to take care of all of the tasks that need to be addressed in making it work. So if it's doing data acquisition, he's got to do the data acquisition, the reporting, the analysis. And when they can build these systems, they build them from the standpoint of, hey, this is maybe the only thing in the laboratory. So they build them as isolated components without really thinking about what the next step is outside their equipment. And that's one of the problems. Without people really thinking in terms of higher level systems and integration of products within the laboratory, you're going to wind up with a lot of systems being put together which are isolated and have no communications capability. There was one system I saw at Pittsburgh conference meeting a couple of years ago where the vendor was really excited about the science behind his work. And when I asked him about the data system, his answer was, well, we just dump everything to an Excel file and it's the user's problem from there on out. We just get the data. Vendors really need to start thinking in steps beyond that, how to help the users work with the data and providing the integration that they need.
Okay. The next question is, what are the major challenges to setting up a fully automated system?
The biggest challenges are space and flexibility. If you think about it, if you were to automate every piece of equipment or every process in your laboratory, you need a huge lab. If things are being done manually, on a given day you pick up one set of piece of equipment, you set it up on the lab bench and you work it and you put it away. When you're done, and the next day that same space on the lab bench is used for something else. If you've got a fully automated system, you don't want to be tearing that thing down every day. What you want to do is build systems that are flexible, where the same hardware configuration might be used for different types of applications, and the only thing that changes are the reagent system programming. That's why the Agilent system is a really nice example of automation. It's a compact footprint. It has a lot of flexibility. It simply depends on the programming. You can use it for different types of analysis and just change the program that's being used to go off and take care of the work. So it's a matter of thinking not just about how I deal with this step and automating it, but how do I deal with the laboratory. We've got to take a much wider view of how we deal with things. And people really aren't geared, don't really deal with that very well.
Okay, and we have time for one more question. How realistic are the possibilities of setting up a sample prep to LIMS data entry system?
Okay, that's getting better. We're, again, because of the points I just mentioned, we're still not there yet. Data communications is a big problem. If you look at it as 3 steps, where you have the sample prep, the instrument, and the LIMS system, when you have things, again, like the Agilent system, it takes care of the sample prep for you. The data system controls the auto-injector. So that problem is kind of dealt with. The next problem is how you get the data from the data system to the LIMS system. There are some cases where we have cooperation and partnerships between vendors that are making that easier to happen. Data format standards and communication systems would make that really easy to deal with, as they have in clinical applications. So it's getting better, particularly since we're dealing with standardized communications protocols at the lower levels like TCP/IP instead of dealing with RS-232 and all the variations of things that can happen with that. We're not there yet. We're getting better. We still have a lot of work to do.
Okay, thanks, Joe. This brings us to the end of today's webinar. Please consider reaching out to Joe directly, as he is the true expert in this field, and I'm sure all of you have his email address by now. I would like to thank all of you for taking time out of your busy schedules to join us today. Watch your emails for information on the video, and we look forward